Today, we're going to be talking about negative feedback op-amp circuits. So before we get into op-amp circuits in particular, I want to talk very quickly about one property of negative feedback. And it will hopefully explain why anytime we want to actually amplify a signal, we're going to use a negative feedback amplifier, okay? So going back to our last class meeting, we developed a relationship that said something along the lines of our closed loop gain, ACL, was our open loop gain over 1 plus or minus our open loop gain times our feedback factor, right? When we had positive feedback, we actually use the negative sign down there because of how our analysis of the signal flow diagram. So negative feedback is going to use the plus sign, okay? So I'm just going to write here for negative feedback, this relationship is going to look like this. So we've got our closed loop gain will be equal to our open loop gain over 1 plus AOL times our feedback factor, okay? Now, for operational amplifiers, which is where we're really focused on in this class, we typically have incredibly high open loop gains on the order of a few 100,000 to a few million. So what we'll see is that this expression for our closed loop gain will reduce to be approximately 1 over our feedback factor K, which essentially means that our closed loop gain will be established by the components that we put in our feedback network, okay? So why this is so important can be explained by talking about what's called gain desensitivity, okay? So when we were talking about our positive feedback circuit or properties of positive feedback in our last class meeting, we worked an example and I showed that for a positive feedback system, a 1% decrease in the open loop gain of the system resulted in a 90% decrease in the closed loop gain of the system, right? So a very, very small change in the open loop gain resulted in a huge change in the closed loop gain, okay? We're going to see the exact opposite thing occur here with negative feedback. So the reason why this is so important is because, and I believe I mentioned this earlier in the class, we might look at a data sheet and see that a typical value for the open loop gain for the op amp that we bought is 100,000. But that is a statistical average, right? The one that we actually bought might be 200,000, or if it was really, really part of a bad production run, it might only be 10,000 or something like that, right? So just because we know what the typical value of the open loop gain is, doesn't mean we know what the actual value is, and it can have a pretty good amount of variation, okay? So gain sensitivity meant that small change in open loop gain gave us a really large change in closed loop gain. Desensitivity, again, is the opposite. A small change in the open loop gain will result in practically no change in the closed loop gain. So as an example, let's consider a system where we have an open loop gain of 10 to the 4 and a feedback factor of 0.01, right? So I believe these numbers are very, very similar to what we used last time. And in this particular case, we would get a closed loop gain of 10 to the 4 over 1 plus 10 to the 4 times 0.01. So our closed loop gain would be 99.010. So our closed loop gain is less than our open loop gain, which is to be expected for negative feedback. Okay. So we went from 10,000 down to about 100. Okay. Now let's consider a case where our open loop gain is 9 times 10 to the 3, while we keep our feedback factor constant. Okay. So this is a 10% reduction in open loop gain. Okay. So 10 times larger of a change than we dealt with in our positive feedback system. When we calculate our closed loop gain here, we would have 9,000 over 1 plus 9,000 times 0.01. And this comes out to be 98.901. Okay. So the change in our closed loop gain in this case, delta ACL. So let's call this ACL1 and ACL2 so I can differentiate between these two things really easily, would be ACL2 minus ACL1 over ACL1 times 100% comes out to be minus 0.11%. Did I do that? So we can see, if I did that math right, which that number actually seems like it might supposed to be 1.1%, but anyway. A 10% reduction in the open loop gain caused a smaller change in the closed loop gain, which means in a negative feedback system, the closed loop gain is going to be pretty damn stable, regardless of how much variation we have in the open loop gain when we purchase our device. Okay. So this is probably the biggest reason why we use negative feedback in applications where we want to actually amplify our signal. So what we're going to do now is we are going to look at a negative feedback amplifier circuit, and we are going to determine some quantities. Okay? So we're not really going to talk about an example of how they're used today, because that's literally what all of Wednesday's class meeting is going to be about. We're just going to analyze one and kind of see what shakes out of that analysis, as well as defining some system parameters we might be interested in whenever we're actually amplifying signals. Okay. So I'm going to start with a classic non-inverting amplifier. So something akin to this. I'm choosing to put my inverting input terminal on top, okay, which makes this node V minus. This node right here will be V plus. Here's the node where I'm going to measure my output voltage. Again, here we'll have VCC plus, VCC minus. So in a negative feedback op-amp circuit, I'm going to have a conductive path between my inverting input terminal and my output terminal, right? So in our positive feedback systems, it was between the output and the non-inverting terminal. Negative feedback, it's between the output and the inverting input terminal. So here's some resistance that I'm going to call R2. Here's R1. And for this particular example, I'm going to ground the left-hand leg of that resistor R1, and I'm going to apply my input signal at the non-inverting input node. And for what it's worth, I'm going to drive some load resistance here that I'm going to call RL. So our op amp parameters are going to be as follows. We're going to have Rn is equal to 1 mega ohm. R out will be 25 ohms. And our open loop voltage gain will be 10 to the 5 volts per volt. For biasing, so these are going to be our resistor values. Let's say that R1 is 5 kilo ohms. R2 is 10 kilo ohms. And RL is going to be 10 kilo ohms as well. Okay. And what I want us to do is find the following quantities. So we're going to find our closed loop voltage gain, AVCL. We're going to find our differential voltage, VD. This one doesn't have any real use. I just want to show you what it is so that we can talk about it a little bit. We're going to find our system's input resistance, Rin. And we're going to find our system's output resistance, R out. Okay. So we're going to use the practical op amp model to do this. And I am going to make an assumption here. I'm just going to assume that Vn is 1 volt. Okay, so you can think about it as if I were applying a 1 volt test source, but just because I want to see how this system behaves. So if I can find V out for a 1 volt input voltage, then my closed loop gain is just V out divided by 1. Okay, so this is just my lazy way of finding the gain since I'm going to have a system and it's going to be a little ugly to deal with. So using the practical op amp model, I could redraw my circuit as follows. Okay. So I'm going to start with my input resistance here. So this is a 1 mega ohm input resistance. And much like I did with my schematic diagram above, I'm going to choose to put the inverting input terminal on top and the non-inverting input terminal on bottom. This is just so that it'll make it easier for me to draw the feedback network in the practical op amp model as well. So that means that this node up here is going to be V minus, and this node down here is going to be V plus, which means my differential voltage VD is going to have positive polarity on bottom since it's always V plus minus V minus. Okay, so just want to make sure everybody's catching what I'm throwing in that explanation there. I'm going to leave the output side of the op-amp model the same. So here's my dependent voltage source. I've got a voltage gain of 10 to the 5. So I'm just going to write 10 to the 5 times my differential voltage here. This is my output resistance, which is 25 ohms. Here's my output voltage for the system, B out. Goodness gracious, excuse me. And now I'm going to make my external connections, right? So the first thing I'm going to do, I can see looking at my schematic diagram, my input signal is going to be placed between my non-inverting input node and ground. So I'm just going to replace or place a voltage source right here. And as I said a minute ago, I'm just going to choose to represent this as a 1-volt source so that when I find V out, I can get my closed loop gain very easily. Between my inverting input terminal and ground, I'm going to have the resistor R1, which is 5 kilo ohms. Between the output node and ground, which I guess I should label ground down here on the bottom, I'm going to have my load resistor, which is 10 kilo ohms. And the last thing I need is my feedback resistor, which is connecting my output node to my inverting input node over here. And that's going to be the resistor R2, which had a value of 10 kilo ohms as well. So before we start analyzing this circuit, is everybody okay with the way that I've redrawn this? Good. All right. So in order to analyze this circuit, I'm going to have to essentially perform nodal analysis. So I'm going to apply Kirchhoff's current law at the inverting input node. So that means I'm going to be adding this current plus this current together. And I'm also going to wind up applying KCL at the output node, which means I'm going to add this current, and this current together. So applying KCL at the inverting input node, do that over here. I'm going to have V minus over 5 kilo ohms. And I'm going to have V minus minus V out over 10 kilo ohms. And lastly, the current flowing to the right is going to be V minus minus V plus, but V plus is just 1 volt with respect to ground. So I'm going to write that as V minus minus 1 volt over 1 mega ohm is equal to 0. Okay. Over here on the right-hand side, I'm going to apply KCL at my output node. So the current flowing to the left is going to be V out minus my open loop voltage gain, which is 10 to the 5, times my differential voltage. My differential voltage is going to be 1 volt minus V minus. All of this will be over 25 ohms. My current flowing up and to the left through my feedback path is going to be V out minus V minus over 10 kiloohms. And my current flowing through my load resistor is just going to be V out over my load resistance of 10 kiloohms. And this will be set equal to 0 as well. So I've got a simple system of equations here, two unknowns, and two equations, two equations and two unknowns, V out and V minus, and so I can just solve this system. So solving this system of equations for those two quantities gives me the result, and I'm going to carry through a lot of decimal points here, and you'll see why in a moment. V minus is 0.9999699 volts. And V out is 2.9999093 volts. So from these results, I can say that my closed loop voltage gain, which is just going to be the ratio of my output voltage to my input voltage, would be 2.9999093 volts divided by 1 volt is obviously 2.9999093 volts per volt, or approximately 3 volts per volt. And my differential voltage, VD, which is going to be V plus minus V minus. Well, V plus is 1 volt. V minus is 0.9999699 volts. So the result of this is 0.00000301 volts, or approximately 30 microvolts. Just for the hell of it, we could also figure out the current that's flowing through our input resistor, right? Just using Ohm's law, that would be VD divided by 1 mega ohm. So we'd have 30 microvolts divided by 1 mega ohm is going to come out to be 30 picoamps. So 30 times 10 to the minus 12 amperes. Practically no current flows into that input impedance. All right. So we figured out the closed loop voltage gain. We also figured out the differential voltage. So the reason why I wanted us to see the differential voltage is because it's a really small number, right? For 1 volt input signal, we get 30 microvolts of differential voltage, okay? So the differential voltage is incredibly small in this negative feedback case. All right. So now I want to find the system input resistance and the system output resistance, okay? So unfortunately, these calculations are going to be a little bit harder to do. So the system's input resistance is typically calculated, and we actually talked about this on the second class meeting. we apply a test source across the input terminals of the system with the output terminals open circuited, which means we're going to reanalyze this circuit with the load resistor disconnected. Okay. So finding lowercase rn, we're going to have pretty much the exact same circuit as before. Here's our 1 mega ohm plus minus VD. Here's V plus, here's V minus. Let's see, this is going to be 10 to the 5 times VD still. $25 ohms goes here. Making my external connections now. So this is my test voltage that I'm going to apply. Once again, it's just going to be a 1-volt source for simplicity's sake. Here's my 5 kilo ohm resistance. Here's my output voltage for what it's worth. I'm not going to put a resistor across the output terminals because to calculate the input resistance, we leave those guys open circuited. Here's my feedback path. And ultimately, what we're trying to find here is this current, which I'm going to call I test, because the ratio of that test voltage, 1 volt, divided by I test will be the resistance seen looking into the input terminals of our system. We okay with that? So just using the test source method to find the resistance of this node. So as you can imagine, we're going to analyze this circuit the exact same way we did a moment ago, because it's the same thing, except that we threw that load resistance away. And we're going to apply KCL at the inverting input node, which will be the exact same relationship we got before, V minus over 5 kilo ohms plus V minus minus V out over 10 kilo ohms plus V minus minus 1 volt, this over 1 mega ohm is equal to 0. Applying KCL at the output node. Now we're only going to have those 2 terms to take care of. So the current flowing to the left through R out is V out minus 10 to the 5 times 1 minus V minus, all over 25 ohms. And the current flowing through the feedback path is going to be V out minus V minus over 10 kilo ohms is equal to 0. Once again, a 2-equation, 2 unknown system, where we would find that V minus in this case is 0.9999700. The out is 2.9999096. And we're going to say that our input resistance is going to be 1 volt, which is our test voltage, divided by our test current. Well, our test current is going to be 1 volt minus V minus divided by that 1 mega ohm of resistance. And if we plug in the value that we got for V minus, we wind up getting 3.328 times 10 to the 10 ohms, or 33.28 giga ohms. Okay. So let's talk about this very quickly. Okay. So another one of the properties, what's up? Oh, Ashton, can you talk or do you want me to look at chat?
I can talk. Okay, so technically the 1 volt source that you put in there, that's different from the 1 volt source we used a minute ago. Now we're using it as a test source.
Yes, but realistically, we were using it as a test source in the previous example as well because we were
Oh,
just interested in finding the gain. So I used
gotcha.
the 1 volt source in the previous example because I knew that if I find V out and divide that by 1 volt, that will be the closed loop voltage gain.
Okay,
This time I'm explicitly using the test source method to find the resistance of this network, which had no connected sources and a dependent source.
okay, thanks.
Okay, we good?
Yep.
All right. For what it's worth, I have all of the Zoom related crap like hidden or whatever. So next time, just talk.
I didn't
Uh,
want to scare
yeah,
anyone.
yeah. It took a student letting me know that you were trying to flag me down for me to even remotely notice what the hell was happening. So just
Got
good.
it.
All right. So we have experienced an increase in system input resistance as compared to our op amp input resistance, right? So we started out with an op amp input resistance of 1 mega ohm, and we now have a system input resistance of 33.28 giga ohms. So that is a 3 million% increase, if my math is correct, in input resistance, right? Mega giga 10 to the 9. That can't be right. Giga is 10 to the 9. Mega is 10 to the 6. Yeah, that must be wrong. So 30,000% increase. But anyway, um, so one of the properties of negative feedback is that we can use it to actually manipulate the input resistance and the output resistance of our system. So in this particular case, we have an increase in the input resistance. What we'll see, based on the configuration of our feedback network, is that we're also going to have a pretty large reduction in our output resistance, which again is really, really good because we're doing voltage amplification here. So in order for us to calculate our output resistance, let me do this down here. And you can refer back to your notes from the second day of class about this. We're going to apply a test source to the output terminals of our system while our input terminals are short circuited. So I'm going to redraw my circuit again. I promise this is going to be the last time. Actually, I don't promise that. We're going to analyze it one more time after this, but we're very close to not analyzing the same circuit over and over again. So here is our input resistance for our amplifier of 1 mega ohm. And once again, this is our non-inverting terminal. This is our inverting terminal, which makes this our differential voltage VD. Here's 10 to the 5 times our differential voltage. $25 ohms goes here. Ground this guy like so. Making my external connections. So I need to short circuit my input voltage signal. So that means I'm just going to short from V plus down to ground here. I need to put my 5 kilo ohm resistor between my inverting input terminal and ground. So that's what I'm doing over here on the left. I need to put my load resistor between my output terminal and ground. So that's this guy right here. Create my feedback path. Which is also a 10 kilo ohm resistor. And then lastly, I'm going to apply my test source across my output terminals. So there's going to be a 1 volt source between my output terminals like so. And now I'm going to try to find this test current. And 1 volt divided by that I test will be the resistance seen looking into the output terminals of our op amp. So I'm just going to have to do one KCL equation here because I only have essentially one unknown voltage in this system, right? The voltage at the output node is now defined to be 1 volt because we put a 1 volt test source there. V plus is tied directly to ground, so that guy's just 0. So the only unknown voltage is that V minus. So if I do KCL at V minus, oops, wrong color. What I'll get is V minus over 5 kilo ohms plus V minus minus 1 volt over 10 kilo ohms plus V minus over 1 mega ohm is equal to 0, which I can solve. And in doing so, I'll get V minus is equal to 0.322 volts. Now that I know that result, I can apply KCL at the output node to solve for I test, where the current flowing in I test will be equal to the sum of the currents flowing out, which will all be expressed in terms of things we know. Okay. So let me just write KCL at output. So I'm going to have I test is equal to, so I'm going to start with this current flowing down. So that's just 1 volt over 10 kilo ohms. The current flowing through the feedback path is just going to be 1 volt minus V minus over 10 kilo ohms. And lastly, the current flowing to the left through the 25 ohm R out is going to be 1 volt minus 10 to the 5 VD. So let me just write this down. 1 volt minus 10 to the 5 VD. Well, in this case, VD is going to be 0 minus V minus. So I'm just going to write that as negative V minus divided by 25 ohms. And if I plug in that value of V minus, I wind up getting I test is equal to 1.329 times 10 to the 3 amps. Now, I want to point something out here. 1.329 times 10 to the 3 amps is 1.3 kiloamps. If we tried to put 1.3 kiloamps through an op amp, it would explode. Okay. So we couldn't ever practically do this. Okay. This is an analysis tool. Okay. So from this result, our output resistance, R out, is going to be once again 1 volt divided by I test, which comes out to be 7.525 times 10 to the minus 4 ohms. So our op amp output resistance was 25 ohms. Our system output resistance is 75 micro ohms. Okay. So we had a very significant decrease in output resistance for our system. Okay. Which again, because we're using this thing as a voltage amplifier, is a good thing. Okay. All right, so thus far, we've talked about calculating open loop gain, or excuse me, closed loop gain, which we successfully did by just analyzing our circuit using the practical op-amp model. We've also made a few observations. So our differential voltage was incredibly small. The current that was flowing into our input impedance was incredibly small. We calculated our system's input resistance and we calculated our system's output resistance. So we could realistically use this circuit containing the feedback network and all of that kind of stuff as a new building block to add other amplifiers and stuff like that too for various applications. And we'll talk about that in Friday's class meetings when we're going to talk about cascaded op-amp circuits. What I would like to do now, since we have, I guess, 30 minutes of class left, is I want to talk a little bit about the ideal op-amp model and all of that kind of stuff and where it comes from. Okay. So we're getting a little bit ahead, but that just means Wednesday's class meeting will probably be short. I don't think you guys will be too broken up about it. Yeah. Break doesn't start till 5 p.m. I got to be here. You got to be here. All right. So I'm going to draw a circuit here, or more akin to a representation of a circuit. Okay. So we're going to kind of take things back to where we started from here for a moment. Okay. So here I have some signal generator that has some associated signal resistance R sig, like so. And this is going to be connected to the input terminals of an amplifier network. Okay. And that amplifier network has some characteristic input impedance Rin. Moving over to the output side of our system, we're dealing with a voltage amplifier. We would have our open loop gain times this amplifier input voltage Vn that I've labeled here. Here is our output resistance. Here's our amplifier's output voltage. And then lastly, I've got some load resistance here, RL. And I'm going to define another voltage here just really quickly. This will be VL for the voltage drop across my load as a function of time. Okay. So taking things back to the basics with regards to amplifiers, okay. The ultimate goal of this system is that the voltage drop across our load resistance will be a scaled copy of the signal V sig that we've applied over here on the left-hand side, right? So in the ideal case, we would say that VL of t will be A, our gain, our system gain, times V sig as a function of time. So what I want us to do is explore how to make this an ideal system, okay? So we have a voltage divider circuit on the left-hand side, and we have a voltage divider circuit on the right-hand side. And we're going to look at both of those networks here individually, okay? So on the left-hand side of things, we could say that our input voltage Vin is just our signal voltage V sig times our resistor ratio Rn divided by R sig plus Rn. Okay. So my question to you guys is, what value of Rn makes all of that signal voltage V sig appear across the input terminals of the amplifier portion of our circuit in the middle?
Have an open circuit, right?
Yeah, exactly right. So if Rn is infinitely large, then Vn is exactly equal to V sig. So this is the ideal version of the input resistance of a voltage amplifier, of which an op amp is a special example of. Okay. Similarly, if we look on the output side, we can see that VL of t is going to be AVOL times Vn, but we already figured out how to make Vn equal to V sig, so I'm just going to replace that with V sig. So we'll have our voltage gain times V sig times another voltage divider relationship, bless you, where this is going to be RL over R out plus RL. Okay. So what value must R out take to make VL just be AVOL, my gain, times V sig?
Zero.
Zero. So when R out is equal to 0 ohms, then VL of T is just gain times my signal voltage. Okay? So this is the second case. Now I'm just going to give you guys the third result, and that is that our open loop voltage gain needs to be as large as possible. So I'm going to say it should approach affinity for an ideal op amp. For what it's worth, let me go back to the very first page here. That's from this relationship right here. If our open loop gain is infinitely large, then we have A over A times K is exactly equal to 1 over K. So for an infinite open loop gain, our closed loop gain will literally just be defined by the elements that we use to bias it. The amplifier itself will have no impact whatsoever. Okay. So that's where that third ideal op or that third parameter comes from. Okay. So what I want us to do now is use these idealized parameters, and now it's really the last time, analyze that circuit that we analyzed at the beginning of the class meeting. So I'm going to redraw our circuit, starting with the amplifier model again. So here is the open circuit for our amplifier input resistance. So I'm just going to make a note here, Rn is equal to infinity. Here's infinity times our differential voltage, where this voltage right here is our differential voltage. There's my short circuit for R out. So I'm just going to make a note here that R out is equal to 0 ohms. And now I'm going to make my external connections. So I'm going to try to find the voltage gain of this system. So just for the sake of making things easier, once again, I'm going to apply a 1 volt source here so that we can just say V out over 1 volts is our voltage gain. Here's my 5 kilo ohm resistor connected between my inverting input terminal and, excuse me, my non-inverting, no, it was my inverting input terminal, sorry, and ground. Here's my feedback resistor. Ten kilo ohms. Here's my load resistance of 10 kilo ohms. Let's take a crack at these. All right. So I want to make an observation really quickly. Okay. Looking at this circuit. Okay. So my output voltage, V out in this case, is infinity times my differential voltage. Everybody see that. I have a voltage source connected directly in parallel with the output terminals of my system. Okay. what I'm going to do is I'm going to algebraically manipulate this. So I can say that my differential voltage, VD, is going to be V out over infinity. Well, what happens when I divide anything by infinity? It goes to zero. So that means if I'm using an ideal op-amp model, my differential voltage is zero. Is that familiar? That's ideal op-amp rule number 2. The voltage present at the non-inverting input terminal must be equal to the voltage present at the inverting input terminal. How much current can flow into my input terminals? 0 amps. That's my other ideal op-amp rule and where it comes from, right? There's an open circuit there. There's no current that's going to be able to flow into my inverting input terminal or my non-inverting input terminal. Actually, so let me write this as I minus the 0 amp, and I'm going to change that one from ID to I plus just for the hell of it. Okay. So I can very easily see that no current flows into the non-inverting input terminal or the inverting input terminal. All right. So from here, really the only thing that I can do is apply KCL at my non-inverting input node. Okay. So applying KCL at my non-inverting input node, I'm going to have, let's see, so V minus must be equal to V plus, which is 1 volt. So I would have 1 volt, over 5 kilo ohms. Then I would have 1 volt minus V out over 10 kilo ohms. Is equal to 0. One equation, one unknown system, solve for V out. That is going to come out to be exactly 3 volts. And from here, our closed loop voltage gain is 3 volts over 1 volt is 3 volts per volt, which exactly happens to be 1 plus R2 over R1. The exact thing we get established completely by just the resistors that we have in our feedback network. Okay. So we're never going to analyze an ideal op-amp circuit like this again, because there's really no point, right? We can use the 2 ideal op-amp rules that we've developed from this. So let me just write those down just for the hell of it. No current can flow into or out of the input terminals of an ideal op-amp. And our second ideal op-amp rule which states that there can be no potential difference between the input terminals of an ideal op-amp. to analyze our schematic representation directly. Um,
But this is only for negative feedback, right?
that is exactly correct, Ashton. These rules only work for negative feedback systems. So just as a very quick thing, we're gonna still get out of here a little bit early. I want us to figure out how much error was introduced by using the ideal op-amp model, okay? So let's say that our percent error is going to be defined as follows. So we want our practical model op-amp gain minus our ideal model op-amp gain divided by our practical model op-amp gain. I'm going to put these in absolute values times 100%. So our practical gain, if we go way back up here, find it, was 2.9999093. Let me grab a calculator real quick. So 2.9999093 minus 3 over 2.9999093. Multiply that by 100. I got 0.003 and some change percent. So using the ideal op-amp model versus the practical op-amp model for this negative feedback system introduced 0.003 of a percent error into our system, okay? In your homework set, I'm going to give you circuits where I'm telling you that the open loop voltage for your op amp or your open loop voltage gain for the op amp is on the order of a few thousand. Okay. And I might also give you relatively low input resistance values and relatively high output resistance values. And what you should find is that even with very poorly designed op amps, in a negative feedback system, the ideal op-amp model will only introduce less than 1% error, okay? So essentially, from here on out, anytime we see a negative feedback op-amp circuit, we should just use the ideal model because it isn't worth the effort of using the practical model because it doesn't produce enough error to really make it worthwhile. All right. So now we're back to a circuits one level of op amps with maybe a little bit of extra stuff thrown in for good measure. All right. That is enough out of me for today. Enjoy your extra 10 minutes of life that you don't have to put up with my bullshit.